Our week 4 materials that you'll find on Blackboard cover population principles. Now recall that a population is any group of organisms of the same species. So this could be a herd of zebras, it could be a classroom of students, it could be a tree of or a stand of trees in the forest. So again, all the same species. Now at some point we'll focus specifically on the human population, but the first thing that we'll talk about is just principles that apply to all populations, no matter the species. So one of the major things that we as scientists want to know that really affect what happens in nature is how large is a population. Do we have a really small population, such as the number of cheetahs on Earth? Or do we have a really large population, like the number of crows? The numbers of these organisms are going to really affect the natural resources that they use. Now, a population grows for a number of reasons, but it can also be limited for a number of reasons. So we're going to talk about two factors: the biotic potential, which is what can we do to reach the maximum amount of reproduction, and environmental resistance. So what is going on that's going to prevent a population from growing? So let's talk about these individually. So first we'll talk about biotic potential. Now, as the name applies, biotic, bio meaning life, and then potential, which you've probably heard that before. Someone has potential. So this is saying your potential for life. In this case, what we're referring to is the maximum rate, and you'll see this referred to as R, at which a population reproduces under ideal conditions. So the maximum rate is going to be different between different organisms, and we'll talk about why here soon. The maximum they can reproduce depends on also the environment. Do they have enough food? Is there little predation? So those ideal conditions mean, are the parents going to be happy and be able to reproduce as much because they have enough food, or they have shelter, or they have any number of things? Now, as I mentioned, this R, or the maximum rate a population can increase, is going to differ between species. So one of the things that's going to affect R is how many offspring does a species have. When one organism gives birth, such as humans, we typically give birth to one offspring. But if you think about dogs, they typically have 5 to 8 pups in a litter. A high birth rate, so how often are organisms reproducing? With humans, it could be maybe around once every 2 years, but if you look at rabbits or birds, they'll mate multiple times a year. Another one is early reproductive age. So the sooner that you start reproducing, that means you're going to create more offspring and increase that population. Organisms that don't reproduce until later in life aren't going to have as high of an R value because their population isn't growing as quickly. And then finally, one thing that will increase R in a species is a fast gestational period. Now, a gestational period is the length of time an organism is pregnant. So for humans, our gestational period is about 9 months, whereas other organisms can be a lot shorter and others can be even longer. Now, if you're not pregnant for as long, that means you can have more offspring, increasing that R. So here's an example. We have an elephant and we have a mouse. Now, elephants, when they give birth, similar to humans, they only give birth to one baby elephant at a time. They'll wait about every 5 or so years to reproduce. If we think about the reproductive age, the females will start reproducing at 14, but they are typically mating with the older males because the older males are the ones that have seniority in the herd. And as far as gestational period, a female elephant is pregnant for about 20 to 22 months. So that's nearly 24 months, which is 2 years. So they are reproducing, and even if they have tons of food and no predators or anything, they're not going to reproduce any faster. So their R is kind of low because they're not increasing their population very quickly. However, a mouse, you'll see that they have 5 to 6 baby mice per litter. They'll have 5 to 6 litters a year. They start reproducing at about a month in age, and their gestational period, or the length of their pregnancy, is about 2 weeks. So their R is a lot higher because their population can reproduce a lot quicker. Now, just because you have a higher R value doesn't mean you're necessarily better. Elephants can live to about 80 years, while mice typically only live 1 year. So sure, they have a much higher R value, but they don't live as long. Now, as I mentioned before, a population will reach its biotic potential, that maximum amount of reproduction, when it is under ideal conditions. Now, environmental resistance is the absence of those ideal conditions. So these are limiting factors that will prevent a population from reaching its biotic potential. So what are those conditions that will make it so that these organisms aren't reproducing, or at least aren't reproducing as much? Well, one is food. If there's not a lot of food, they're not going to be able to support as many young. They may not reproduce at all, so your reproduction rate is going to drop. Another one is disease. So especially when you have many organisms in an area, disease spreads a lot faster. There's a lot of disease around, you're probably either not going to be able to reproduce or be too weak to reproduce. If predation is very high, more than likely you won't be reproducing because you'll be using so much energy just to hide from the predators. One could be a lack of space. So even if you have, say, a population of zebras, if there's not enough space for them, if they're crowding, or maybe they don't have a breeding territory, they're not going to be able to reproduce as much. And then finally, and kind of tied into number 4, is habitat destruction. So if humans are going to chop down the rainforest, there's a lot of organisms in the rainforest that use the trees, the ground, all sorts of parts of the forest for reproduction, a breeding ground, or maybe building nests, or just living. So if they have less habitat, they're not going to be able to continue to reproduce and support the individuals in their population. So again, these are limiting factors that are going to prevent a population from reaching its biotic potential. So a way we can kind of map how a population is growing is by looking at graphs, a graph of that population. So before we even talk about J-curves, take a look at this graph. On the x-axis, again, that's the horizontal axis, we have time. So this could be a couple days, it could be a couple weeks, couple years, decades, etc. And then on the y-axis, so again, vertical axis, we have the population size. So how many individuals are in this population? Now there's two kinds of ways a population can grow. One is through a J-curve, and that's what you're seeing here. It got its name because of the way it looks. Early in time, we have this very slow increase in very few organisms, and then all of a sudden we start shooting up, and it continues to go higher and higher. Now, for any of those who have taken a math course that have seen a graph like this is considered exponential growth. So what that just means is that you have a slow start, but then you start growing very, very, very quickly. And that part is called the exponential growth. You'll also hear unregulated growth. So if we think about the population itself, let's think of this as a population of mice. This is saying there's nothing restricting those mice at all. They're going to keep reproducing as much as they can over and over. Now let's think about this scenario in terms of biotic potential and environmental resistance. So in this case, we have lots of biotic potential. This population of mice is reproducing as much as they can. There's nothing stopping them because their population keeps increasing. On that same token, there's very little environmental resistance. You don't see their population going down at all. We don't see anything that's preventing this population from continuing to reproduce or to slow down reproduction. Now, if this population keeps growing higher and higher, taller and taller, more and more individuals, what do you think will happen? Well, more than likely, what's going to happen is we're going to see a crash. That this population can't keep growing exponentially. There's going to be way too many organisms. A lot of organisms is going to lead to reduced food. If you have 20,000 mice all eating similar things, yeah, they're going to end up running out of food. You're also going to see, if we think about mice, there's going to be less places to live and to breed. If you think about 20,000 mice in a house, that house is not going to be able to support that many mice because there's just no room for them. When you have a lot of individuals, disease and parasites spread really quickly. If you think about, cats or dogs in a pound, if one of them have fleas, they're all going to have fleas. If one of them gets sick with something, they're all going to get sick with something because they're in close quarters and disease and parasites can spread very quickly. You'll also notice that predators will go up. Oh, we have tons of mice. Well, the owls that were predating on those mice have something to eat now. Well, now they're going to find these mice. Those owls are going to reproduce. The little baby owls are going to eat mice. And so you're going to have more and more predators if you're having more and more prey. So here's a real life example of a J-curve that leads to a crash. Now this is based on two different organisms. We have the lynx, which is this cat, kind of like a bobcat, and a snowshoe hare, so a rabbit or a bunny, etc. Now on this graph, notice this is very similar to our other population graphs. We found time, so in this case we have the year, so 1845 to 1935. This is on the x-axis. And we have population, in this case population in thousands, on the y-axis. So these two lines, the green line, so this one along here, is representing that rabbit, that snowshoe hare, whereas the lynx is this red line. So let's take a look, say here in about 1863. We start seeing a huge rise in these snowshoe hares. We're seeing this J curve. Now, it doesn't start nearly slow, but this huge increase, that's very characteristic of a J curve. But notice what happens. We have a huge crash in them. You couldn't keep growing exponentially because it's going to lead to a crash. Now, in this case, the crash may have been due to reduced food or disease or less places to live. We don't know. But we do have evidence that it could be due to more predation. So this red line represents this lynx. And again, the lynx is eating on these snowshoe hares. So you see that here we have the rabbit increasing a lot. Well, the lynx who eats these starts increasing after we see this peak. So they're increasing because, oh, they have more food, they're fat and happy, they can reproduce, their young are fat and happy, they can reproduce, etc. So you see this huge spike in predation, which then leads to the crash of the snowshoe hare. Now, since the snowshoe hare, or that prey base, is declining, so will the lynx population, because they no longer have that much food. They overhunted them, so to speak. They were hunting and hunting, they reproduced, they continued to hunt, and then they started running out of food. So they too crashed. And you can see this trend happens every few years. Here the the hare